Okay, one of the important mechanisms in the alkyne chapter is the tautomerization of enol to ketone or aldehyde. And so what this reaction is telling us, or what this question is asking us to think about, is that tautomerization can happen from a base catalyzed perspective or from an acid catalyzed perspective. And so what we have to do is we have to be able to think about how this tautomerization from an enol to a carbonyl can happen from either one of those two possible structures. And so it's asking us to show that mechanism in that process. So let's start off with the acid catalyzed hydration or tautomerization. So the first thing that's going to happen is my double bond is going to come out and do a proton transfer, and that's going to allow me to form an intermediate carbocation. Now, I've still got the OH group here. And of course, now I'm forming the more stable carbocation in the secondary position. Now, there's going to be some resonance that I can show with that OH group right next to the cation. I can show a protonated carbonyl group as one of the resonance structures. Like so. And then finally, a water can come along and deprotonate that carbonyl group, and that's what forms the neutral carbonyl product. Okay, so one of the important pieces of this particular mechanism is to keep in mind that only species that are positively charged can form in the intermediates of a reaction that would be acid catalyzed. You can't form anything that would be negatively charged because they're not compatible. But in the other example that we're going to do now, it is a base catalyzed reaction. And in that case, we do form negatively charged intermediates. What we can't form is any positively charged intermediates in that case. And so I have that's what helps me think about how the reaction can take place. So I can't do a nucleophilic attack, and I can't, which would form a cation from the hydroxide, because that's not compatible with the conditions of the reaction. But what is compatible with the conditions of the reaction is having the OH group form remove that proton and form this species of negatively charged oxygen. An enolate ion is what it's called. Now, what's similar is that the enolate ion is also a resonance contributor. I can show that negative charge moving down onto the carbon. And now that I have that negative charge on the carbon, a water can come around and donate a proton to that location to reform the OH group and get me to my final product. Okay, it's important to know these reaction mechanisms, and so be sure to consider them. And again, remember, one of the important parts to think about in these reaction mechanisms is to form intermediates that are compatible with the conditions.